In this lesson video, we're going to be talking about day 6.3. We're going to talk about circle segment theorems and the relationship between different segments as they intersect our circles. Real quick, kind of going back to our previous lesson, we talked about angle relationships when we have certain segments intersecting circles, the angle to arc relationships measured in degrees. Well, our pictures are going to look very much the same as things we did in these examples, but we're going to look at the segment relationships instead. So the first thing I want us to remember are the different kinds of segments that could possibly intersect a circle. And we're going to focus on three in particular. First, we're going to focus on what a chord is. So we're going to start by drawing a chord. Remember, a chord is any segment with endpoints on the circle, and it only exists inside the circle. This is a chord. And then we're going to look at what a tangent is. So I'll draw an example of a tangent. A tangent is a line or segment that intersects the circle at exactly one place. Okay, it could continue on outside the circle like that, but it never goes inside the circle. So this is a tangent. And then a secant is a line that goes through a circle twice, but goes inside and outside. So this is an example of a secant. And as we look at the picture to the right here, we can also look at a given picture and identify these parts. So if I go back to our chord, this would be an example of a chord, JL. The tangent we have in this picture is the segment GJ, not GI, GJ. It only intersects the circle at point J. And then the secant is this line. We only use the endpoints to label it though, G and I. So segment GI is a secant. And so we're going to use these kinds of terms, chord, tangent, and secant, and look at the relationships between their different intersections. So the first one we're going to identify is the concept of tangent, tangent. When two tangent lines intersect. Now, two tangents are always going to intersect outside of the circle. When a tangent intersects another tangent, it creates these tangent segments that are always equal. So our formula is pretty easy to remember. Tangent equals tangent. One tangent segment equals the length of the other tangent segment whenever they intersect. So in this case, the length of AB has to be the same as the length of BC. The next one we're going to look at is when two secants intersect. When two secants intersect, they create a relationship that looks kind of like this. Where I have got an inside and an outside part of each secant. But we're needing to understand that the two inside and outside parts here, A and B, go together. They're part of the same secant. And C and D are part of the same secant. Now, this formula uses this outside times whole equals outside times whole. So when it says the word whole there, that means the entire secant segment that I have, the inside and outside part together. To find the whole amount, be sure to add both parts of the segment. Okay. So that entire segment is the expression A plus B. Remember, part plus part equals whole. So when I say outside times whole for that top secant, the outside portion is A. The whole amount is A plus B, not times, A plus B. And for the other side, the other secant, the outside part is C, the whole thing is C plus D. And so as we move on to look at two chords intersecting, this is a little bit different. Our formula for two chords intersecting is part times part equals part times part. Now, when I say the two different part words here, this first one, part times part, comes from the two parts of the same chord. And the other side, the part times part, are the two parts of that same chord. So when I say part times part here, for the first two, that's A times B. A times B. The other side of that part times part is C times D. Okay? And then this last one is the relationship of a secant and a tangent. Now, when I am using a secant and a tangent, the formula is this. The secant part of this is still the phrase outside times whole. Anytime we use a secant, that's how you're going to calculate that, outside times whole. So that would be part B times the whole thing, B plus C. But because the other portion is a tangent, the outside is A, and the whole thing is A. So outside times whole really makes it A squared. That's why this side is A squared, or outside squared. Because outside is the same as the whole thing. So all we have to do for our problems here is identify which of these theorems, which of these formulas we should use. So for this first one, this is an intersection of two chords. Both those segments are chords. So the segment theorem is chord, chord. And the formula is part times part equals part times part, where the first part times part is going to come from one of the chords. So 14 is one part times the other part, 15. And that has to equal the same as multiplying the other two parts, x times 10. We can simplify. 14 times 10 is 210. Or sorry, 14 times 15. I apologize. 14 times 15 is 210. And that equals x times 10, I'm going to write as 10x. And then I have to get rid of that 10 with the x. I have to undo 10 times x. So we divide by 10 on both sides. 210 divided by 10. Think of it as the zeros canceling. That's just 21. Okay? So that's your chord-chord theorem. For the next one, example 2, our segment theorem. These are both secants. They have an inside and an outside part. Both of them do. So this is the secant theorem. And our formula for secant is outside, I'll just write the word out, times the whole thing for one secant has to equal the other outside times the whole thing for the other secant. So if I choose to do JL as my first secant, the outside part is 10. The whole thing is 42 plus 10. Remember, we get the whole thing by adding them together. For the other secant line, the outside part is 13. The whole thing is x plus 13. Now, I want you to be very careful. X plus 13 inside here, this does not equal 13x. You have to leave that as x plus 13. The only thing we can do on this side is distribute this outside 13 to both of them. On this side, I can distribute, or I could just combine these since I know both numbers. 42 plus 10 is 52. So I can do the 10 times 52, which is 520. And on the other side, when I distribute 13 times x and 13 times 13, I get 13x plus 169. And to solve this for x, we start by subtracting the 169. And 520 minus 169 is 351. And that equals 13x on that side. So we just divide by 13 to find out what x is. Okay, and that gives me, that with the calculator, 351 divided by 13, 27. Okay, so that means x is 27, but now they want me to use that to go ahead and find the full length of NL. That means I'm going to take my 27 and I'm going to add that outside 13 to it. And 27 plus 13 is 40. Okay, let's keep moving right along. On number 3, this is another type of problem, but this time we're using tangents for both lines. Each of these lines is a tangent. So my tangent is my theorem. You can abbreviate like this. And that one's one of the easiest formulas. The tangent of one has to equal tangent on the other. Tangent equals tangent. So this equals this. 43 minus 2x equals 12x plus 1. and we start to solve this for x. We first add the 2x to both sides, leaving 43 equals 14x plus 1. Then we subtract 1 from both sides. We get 42 equals 14x. Divide by 14, and we get x equals 3. Now, since x equals 3, they want the length of xy. They want that tangent length. So I'm going to plug in my 3 for x here. 12 times 3 is 36. And then I add the 1, and I get 37. Okay. One more example. The only one we haven't done yet is a secant tangent. And that's what this one is. This relationship, this segment theorem, is secant tangent. Because one of the lines is a secant, 16 inside, 9 outside makes that a secant. And then this other portion is just a tangent. So that formula for the secant side of things is, again, outside times whole. But the tangent side of things is the tangent, or the outside part, squared. So for the secant, the outside portion is 9. The whole thing would be 9 plus 16. But for the outside portion of the tangent, that's 3x squared. Remember, that means 3x times itself. So when I do 3x squared, I actually need to think of it as 3x in parentheses squared to make sure that I end up doing the 3 squared as well. So that's 9x squared. On this side, I still have a 9 out front. Let's go ahead and add those inside, though. 9 plus 16 is just 25. Okay, now there's a couple things you could do, but I do want you to notice this. I've got a 9 as a factor on both sides. Those should cancel. Okay, or I could kind of go about this the long way and do 9 times 25 is 225. But then I'm going to divide by 9 anyways to get rid of that. And so it goes back to being 25 equals x squared. So I need to take my square root to get x by itself finally. And the square root of 25 is 5. So the length, or the value of x, is 5. Okay, if you turn the page in your notes, you'll see another set of examples. The next 4 of them are just different versions of these same kind of problems. I want you to pause the video here and try these next 4 completely on your own. Okay, pause the video, try and do the next 4, and then if you get stuck or when you have all 4 of them done, you want to check your answers, go ahead and click play. If you need more time, keep the video paused here. Otherwise, these are the answers we should get for the next 4. And I'll go one at a time. On number 5, we should get x is 15. This is a secant-secant relationship. Okay, and so we do outside times whole equals outside times whole. But what I want you to pay attention to, when it comes to this secant, and I do outside 9 times the whole thing, 9 plus x, this 9 plus x is not 9x together. The only reason I get a 9x here in my next line is because I'm doing the outside 9 times the x and times the inside 9. So we get 81 plus 9x. Okay, so if we didn't get that, if you got a different answer here at all, chances are you may have thought that this 9x here was 9 times x, and that's not true. Okay, we can't just turn that into 9x. I have to leave it as 9 plus x and distribute into that. So I get x is 15. On number 6, again, you might have gotten a different answer here, and you want to be careful. This is chord, which means part times part equals part times part. For one of the chords, part 6 and part 6, that's just 6 times 6, 36. But for the other chord, I'm going to do the part that is 4 times the entire other part, 5x minus 1. That means I have to multiply 4 by the 5x and the minus 1. And so I write that in parentheses like this to show myself, to remind myself that I need to distribute to both of those. So we should get 20x minus 4 for that side. And we solve that and we get x is 2. And then they ask for the length of dB. So if I plug in 2 here for x, 5 times 2 is 10. 10 minus 1 is 9. That 9 plus the other side 4 equals my total 13. Okay. All right, number 7. This is a tangent again. So part equals part or tangent equals tangent. And so 8x minus 19 equals 5x plus 23. If you solve that, you should get x is 14. And when you plug back in for AB, that should be 93. Okay, one other one that you're supposed to try on your own, and that's number 8. This is another secant tangent problem. The secant has two parts, the inside and the outside. So the outside part is 8. So for your equation, we're going to do outside times whole thing. Now the whole thing, we have to take that 5x minus 1 and add the 8 to it. Okay, that's kind of what I did here in a little bit different order, but that does combine to 5x plus 7. Then I distribute into 5x plus 7, and I get 40x plus 56. The other side is that outside portion of my tangent squared. 16 squared is 256. So I subtract 56 from both sides, divide by 40, and I get x is 5. Then when you plug back in, they only want NP. NP is just the inside part of the secant. So all I have to do is plug in here. 5 times 5 minus 1 gets me 24. Okay, as we finish up this lesson, there's one other idea we want to talk about, and that's a problem like number 9. On number 9, okay, they ask you to find the perimeter of this triangle DEF. Now you'll see that the triangle DEF, the sides of that triangle all touch the circle at exactly one place. Okay, DE touches the circle once at H, EF touches the circle once at I, and FD touches the circle once at G. That makes every side of this triangle a tangent. And so the segment theorem I'm going to use is tangent tangent, because these are all tangent lines. And in order to find the perimeter, I'm missing some pieces. I'm missing this length, this one, and this one. And I'm just going to add all those up. Well, what you notice is DH and DG are tangent segments that have to be equal. That means DH has to be 11. Okay. In the same way, HE and IE are tangent segments that have to be equal. So that one's a 16 as well. And at the bottom side here, GF and IF both have to be the same 9.5 because they're tangent segments. And remember, tangent equals tangent. So the sides that make up my triangle are DE, which is 11 plus 16, or 27, and EF, which ends up being 16 plus 9.5, and 16 plus 9.5 is 25.5, and FD, which is 9.5 plus 11, or 20.5. So if I add all three of those together, that gives me my perimeter. And when I do add those three numbers, I get the total of 73. So your perimeter of that triangle is 73. One final example here. Same idea we just did, but this time instead of a triangle around the circle, I'm dealing with a quadrilateral. 4 sides. Again, the segment theorem is going to be the same thing, though. These are all tangent lines. So my segment theorem is still tangent tangent. But it gets a little more complicated because these parts that are equal to each other now, I'm using some other variable expressions. Now, I did not put a point, or I didn't label the point where each tangent touches the circle. So I'm just going to put dots there to help show that breaking point. But I do know that this length of 9 has to match this other length down here. So I can go ahead and write 9 there. But for the rest of these, I have to do a little bit of work. This length up to P and the other one on the other side have to be equal to each other. That lets me know I can set up an equation. Y plus 2 has to equal 3y minus 10, because tangent tangent tells me each tangent segment is equal to its matching tangent segment. So I can subtract y from both sides. So I get 2 equals 2y minus 10. Then I add 10 to both sides. 12 equals 2y. Divide by the 2 on both sides. And I get y equals 6. Now, if you wanted to find the x first, you could have done that. Let's say I wanted to find x. These are also tangent segments that have to be equal. So I can say x plus 4 equals 5x minus 8. And I can solve this for x. I can do minus x from both sides. and get 4 equals 4x minus 8. Then add 8 to both sides. On the left, 4 plus 8 is 12. So since 12 equals 4x and I divide by 4, 12 divided by 4 is 3. So I know x is 3. Now, what I need to do with each of those numbers, back here with the x's, I need to know, since x is 3, I can plug it in here. 3 plus 4 then is the length 7. So that side's 7 and this side would be 7. So I've got 2 7s there. Up here for the y values, y was 6. So I can plug in the 6 for the y there. 6 plus 2 is 8. So this is 8 and this is 8. Now there's only one section I have left, and that's both these segments over here at Q. From here and from here, those are both equal to each other, but I don't have a value for either one written down. But they do tell you this entire length from P down to Q is 13. That means that this section here can be found by taking 13 minus that 8. And 13 minus 8 is 5. So this is 5 and this is 5. Now I have enough information to find my perimeter. The individual side lengths are SP. S to P would be 9 plus 8, or 17. P down to Q, we know that total already. That's the total 13. Q back down to R is 5 plus 7, or 12. And R back up to S is 7 plus 9, or 16. So my perimeter can be found by adding these 4 together. 17 plus 13 plus 12 plus 16. When I add those up, I get a total of 58. So the perimeter of this quadrilateral is 58. Okay. If you need any more assistance with this, send me a message in Canvas or find me in class and we'll talk about it. But this covers the lesson of circle segment theorems.